Yeah, today we are very pleased to have Dr. Ting give the first seminar. So the introduction will be short, mainly because, as you may know, Ting joined our department as an assistant professor in July. So I guess most of you know about Ting. And she earned her PhD degree at UW-Madison in the Department of Statistics, and then did a postdoc at UPenn in the Department of Statistics and Data Science. And here we are. So Ting, thanks again for accepting our invitation. And yeah, we look forward to your talk.
Thank you so much, Yadi, for the nice introduction. Let me share my screen. Can you see my slides okay?
Yeah.
Yeah, great. Yeah, thank you so much, everyone, for coming. I'm really thrilled to have the opportunity to talk here for the first time as a member of this department. And I'm also especially excited to talk about the work that I really like, where we propose a beautiful solution to two salient challenges in Mendelian randomization. This is a joint work with Dr. Jing Shao and Dr. Han-Sang Kang from University of Wisconsin-Madison. And this is the paper that this talk will be mostly based on, and it's just published in Annals of Statistics. This is the outline of today's talk. First, I'll introduce instrumental variable and Mendelian randomization. And then the main focus of today's talk will be based on the D-bias inverse variance weighted estimator in the Mendelian randomization with only summary data. And specifically, I'll talk about how the IVW estimator addressed the two challenges, the many weak IVs and the balanced horizontal pleiotropy in Mendelian randomization. First of all, this talk is about causal inference. And we probably all know that association is not causation. But here I just want to briefly illustrate using an example. So the common sense tells us that dog obesity is associated with human obesity. However, intervention on dog does not reduce owner's weight. So there's no causal effect of dog's weight on dog's owner's weight. And in this interesting cartoon, it illustrates that if the dog's owner let the dog to exercise, this will not reduce the dog's owner's weight. And the reason behind this little story is that although there's no causal effect of dog's weight on dog's owner's weight, they are confounded by a lot of things. For example, lifestyle. For example, if the household eats an unhealthy diet and does not exercise, this will increase both the dog's weight and dog's owner's weight. And in observational studies, it's very hard to measure all the confounders, and there will be unmeasured confounder. And in this case, without further information, we cannot identify the causal effect. In the language of linear regression, suppose we have an unmeasured variable u that affects both x and y. Even though the x has no causal effect on y, we will still observe a spurious association. That is, the covariance of x and y are non-zero. And causal inference in the presence of unmeasured confounding seems hopeless. Without random experiments, we may be comparing apple to orange. But luckily, in real life, there are many randomness going on, which can be cleverly used to identify the causal effect. So the Nobel Prize in economics this year goes to the three who find experiments in real life. And one of their major contribution is on the method of instrumental variable. Instrumental variable is a device to deal with unmeasured confounding. So for a variable to be an instrumental variable, it needs to satisfy three core IV assumptions. The first one is that this variable z needs to be related with the exposure variable x. And the second is randomness. The z is independent with the unmeasured confounder u. And the third one is exclusion restriction, which says that z has no direct effect on the outcome. And with these three core IV assumptions, we are able to partially identify the causal effect, which means we can bound the causal effect, but we are still not, we still cannot point identify the causal effect. And we usually need an extra assumption for point identification. And some popular ones are assumed assuming an extra linear model or monotonicity or no additive treatment IV interaction on the treated. When we think about the IV assumptions, I always think it's helpful to cast those assumptions into a prototypical setting, which is in the case of non-compliance in randomized controlled trial. Suppose we are interested in the effect of vaccine on the outcome, and then we run a randomized controlled trial that randomly assign patients to the treated arm or the placebo arm. But when patients does not comply to the treatment they are assigned to, so we have non-compliance, and the decision that people do not comply to the treatment may be related to something that that's also associated with the outcome. So how do we identify the causal effect of the vaccine status on the outcome? So actually, we can use the random assignment to the treatment arm at this variable z as an instrumental variable. And it's easy to justify these three core IV assumptions in this prototypical setting. So the first assumption, relevance, hold if the randomization is effective and is related to whether this person gets vaccinated or not. And because the z is randomly assigned, so z is independent with the unmeasured confounder u by design. And the exclusion restriction is also true, which says because the treatment assignment has no direct effect on the outcome. And this will hold if we are in a double-blinded controlled trial. And in observational studies, it will be hard to find instrumental variables that satisfy these core IV assumptions. Let's suppose we want to study the effect of BMI on CAD. How do we find an instrumental variable that satisfies these assumptions? So in fact, there is a brilliant idea called Mendelian randomization that says we can use the genetic variants as instrumental variables. And intuitively, the nature is running a randomized experiment for us because we inherit the genetic variants from our parents randomly. And also people who inherited a certain allele will have naturally higher BMI. And the randomization, in summary, the Mendelian randomization is using the genetic variants as instrumental variables. And the Mendelian randomization is named after the great scientist, Gregor Mendel, who established the law of the Mendelian inheritance. So Mendelian randomization is a method that uses genetic variants, also called SNPs, short for single nucleotide polymorphisms, as IVs to assess whether a modifiable exposure X exerts a causal effect on an outcome in the presence of unmeasured confounding U. And hereafter, I'll use the genetic variant and SNP and IV interchangeably. The most common design of the Mendelian randomization is actually the two sample summary data Mendelian randomization, which basically use one summary data for the exposure and one summary data for the outcome to identify the causal effect. And the main reason for its popularity, I think there are two reasons. So the first one is that it's based on summary data. So it bypass the need for us to obtain individual genetic variants data. And this largely alleviates the privacy concern. And the second reason is that because it's a two sample setting, so we can use the GWAS data that are available publicly in a very flexible way and to study the causal effect of any two traits of interest. Let's see an example. If we are interested in the causal effect of BMI on the risk of CAD using 1,119 independent genetic variants, then the only thing we need is to collect an exposure data set and an outcome data set. And the exposure data set is a GWAS for BMI in the UK Biobank. And from the exposure data set, we obtain the marginal association statistics and the standard error that are obtained from fitting a regression of the BMI with respect to each individual genetic variant. And similarly, for the outcome data set, is a GWAS for CAD, and we also obtain the marginal association statistics and standard error. And these two data sets are independent because their population are non-overlapping. So the data will look like this. although we have more than 1,000 genetic variants here, I'm only showing 5 of them. And for each genetic variant, we record the exposure, the exposure status. So the effect of the genetic variant on the exposure, which is little gamma j hat, and the standard error. And we also have the capital gamma j hat and the standard error. To build intuition on how we use these summary statistics to estimate the causal effect, it's helpful to start from a linear structural equation. So suppose we have an exposure model which says the X is related to the P genetic variant in some unmeasured confounder U in some random error. And the outcome is related to the exposure and the also the unmeasured confounder and random error. So the causal effect of X on Y is beta 0. So recall that we assume the genetic variants are instrumental variables. And the first assumption that they need to satisfy is that the little gamma j hat cannot all be 0. So at least one of them needs to be non-zero. This is a relevance assumption. And the second assumption is that the genetic variants need to be independent with the unmeasured confounder U. And the third assumption holds in this case because in the outcome model, we no longer have the genetic variants. This is because once we condition on the exposure, the genetic variant has no direct effect on the outcome. And under these two models, we can plug in equation 1 into equation 2, and then we immediately get a reduced form, which relates the outcome to the genetic variant Zj, and the coefficient is denoted by capital gamma J. And from these two linear structural equations, we can motivate the following assumption, which assumes the little gamma j hat is centered, follows a normal distribution that's centered at little gamma j. And also the capital gamma j hat is centered at beta 0 times little gamma j. So the normal approximation is reasonable due to large sample size. And they are centered, at little gamma j and beta 0 times little gamma j because of the independence of Z1 to ZP. And outside the linear structural equation, for example, when Y is binary and follows a logistic model, then beta 0 can be interpreted as a conservatively biased quantity for the causal odds ratio. And in general, the beta 0 can be interpreted as a local causal effect, which means how the expected outcome will change if we do a little perturbation on the exposure variable. And from this assumption, naturally, we can calculate the so-called ward estimator or ratio estimator denoted by beta j hat. And this beta j hat is centered around beta 0. So for each genetic variant, we can obtain a ratio estimator that is centered around the causal effect beta 0. But now we have P genetic variants. So it's natural that we want to combine them together. And a straightforward way is to use the inverse variance weighted estimator. So basically, we just combine these P ratio estimators using a weighted average, and the weight is the inverse of their variance. So this idea is originated from meta-analysis. But in the Mendelian randomization setting, empirical evidence shows that the IVW estimator is biased when we have weak SNPs. And to mitigate the bias, practitioners usually pre-screen for strong SNPs using the genome-wide significance p-value, which is 5 × 10⁸8. And then using the selected strong SNPs to plug into the IVW estimator. But I would argue this is only a bandit solution because it only mitigates the bias, but not resolve the bias. The bias of the IVW estimator is because it does not address the two salient challenges in Mendelian randomization. The first one is the many weak IVs. So in the genetic setting, each genetic variant is usually only weakly associated with the exposure X. So the variance it can explain is very small compared to the variance of these traits. But we have a large number of such weak IVs, so we are in a many weak IV setting. And the second challenge is the pleiotropy, which means that each SNP has multiple biological functions that affect other variables beyond the exposure variable. And this violates the exclusion restriction assumption for these SNPs to be valid IV. because they have direct effect on the outcome. There are many existing works that try to deal with these two challenges. So for the many weak IVs, it is well acknowledged in data randomization, but mostly studied empirically. The issue of weak IV is well studied under individual data setting in econometrics, but we are in a summary data setting. And MRREPS is a method that's robust to many weak IVs. And for the second challenge, the widespread horizontal pleiotropy, some methods would assume that there exist some valid IVs, and some will assume that the direct effect of the IV on the outcome is IID follow a normal distribution with mean zero. So this is essentially balanced horizontal pleiotropy. Or this uncorrelated pleiotropy, which means that the direct effects are not necessarily centered at mean zero, but they need to be independent with the IV strength. So this is the inside assumption. Or some would assume mixture model. But as we can see here, the only method that's able to deal with both challenge is the MRREPS. And MRREPS is a great method, but admittedly, it's a little more complicated compared to the IVW estimator. So I would argue that it's a multi-injection cure. So we have the banded solution, that's the IVW plus pre-screening, and also a MRREPS, which is a great method, but it's more complicated. So what we will propose is a debiased IVW estimator. It is a one pill cure. And in this age where, in this days where we need vaccine campaigns, and we know more than ever the power of a simple solution to complicated problems. So next, I'll move to the debiased inverse variance weighted estimator. We impose two assumptions. The first assumption is the key for identification. So it assumes first that the 2p genetic variants, the 2p coefficients from the genetic variants, they are normally distributed. This is a reasonable assumption from large sample size. And then the two sample design will make sure that these two data sets, they are independent. And also because of the mutual independence of the genetic variant, we have these 2 times p coefficients, they are mutually independent. And also we assume that the standard errors, the standard deviations of the marginal association statistics are known. And this is also due to large sample size. And it's a reasonable approximation when we have the number of genetic variants smaller compared to the sample size. And for first of all, we assume that there's no pleiotropy. So we have the capital gamma j equal to beta 0 times little gamma j. But later, this assumption will be relaxed. And the second assumption says that there exist positive constants such that the standard deviation ratio is bounded. So let's see what this assumption means. So first, we can calculate that the standard the variance of the marginal association statistics have this form, and then the ratio of these two leads to something like this. And because this is the variance that the genetic variant can explain, and this is the variance of these complex traits, so usually this term will be very small compared to the variance of like BMI or CAD. And in this case, this ratio is approximately variance of X over variance of Y times the ratio of the sample size. So this assumption too is reasonable as long as we have the sample size in the two data sets are of similar order. So in summary, assumptions 1 and 2 are reasonable for both common and rare genetic variants. And before I move to the formal results, we will need to define a crucial quantity, which is the IV strength. So here, let's define mu j as the z-score of IVJ's effect on the exposure. So this encodes two notions of weak IVs. The first one is that the coefficient itself is very small. And the second is that the standard deviation is very large, which is basically due to rare variant. And then when the IVs are strong, we basically have the z-score squared which is of order the sample size. And when the IVs are weak, we will have the z-score square is much smaller compared to the sample size, or it's of constant order. And when the IVs are irrelevant, this z-score is equal to 0. So actually, this individual z-score is not so crucial here because we are essentially aggregating all the genetic variants. So what's crucial here is the quantity called average strength of the IVs, which is basically the average of the z-score squared. And this kappa, like the z-score itself, could range from 0 to something of order the sample size. And we can estimate the kappa in practice, and the unbiased estimator of that is the average of the F statistic minus 1. Now we are ready to study the asymptotics of the popular IVW estimator. And we develop a phase transition of the IVW estimator. So the first regime we consider is that the average IV strength divided by the number of SNP goes to infinity. And also the number of IVs goes to infinity. And this is a technical condition, a Lindenberg type condition to guarantee the asymptotic normality. So this regime A is the only regime where the IVW estimator is consistent and asymptotically normal. In the regime B, if we only have the average IV strength goes to infinity, then the IVW estimator is consistent. And in regime C, if the average IV strength converts to something to a constant, then the IVW estimator is biased towards 0 because it converges to beta 0 times something smaller than 1. And if the average IV strength goes to 0, then IVW estimator will converge to 0, regardless of the true value of beta 0. So the IVW estimator is consistent and asymptotically normal when all the IVs are strong in common variants and when the sample size is much larger compared to the number of SNPs. But in practice, we are usually in regime C, which is the average IV strength is something smaller than 10 or 20. So it's reasonably in the regime C, where the average IV strength is a constant. So that's why we observe that the IVW estimator is usually biased towards 0 in practice. But let's take a closer look at the IVW estimator. So we can write the difference of the IVW estimator with respect to the causal effect of interest. And then we can calculate the expectation of the numerator equals negative beta 0 times something positive. And this is, so this means that the difference of IVW estimator compared to the truth is not well centered at 0. And then we can also calculate the asymptotic bias of the IVW estimator, which is of order negative beta 0 divided by kappa plus 1. So this explains why the IVW estimator is biased towards 0 in two-sample Mendelian randomization, and also why the consistency of IVW requires kappa goes to infinity. And for asymptotic normality of the IVW estimator, we require the asymptotic bias over the standard deviation goes to 0. So this translates to kappa over P goes to infinity. So the source of bias from the IVW estimator is actually from the measurement error in the little gamma j hat. So this is because if we set this sigma xj to 0, then there's no bias. And in the weak IV setting, it's crucial to center our estimator to tightly around the truth. Otherwise, any small bias will be amplified because the strength of the IV is very small. So the denominator becomes very small. But we still do not want to get rid of give up IVW estimator yet, because it has some desirable properties. First of all, it's very popular and it's widely accepted. It's one of the most used Mendelian randomization method in practice. And it's easy to understand and it can be computed very fast. And it also has always has a unique solution, which is in contrast to recent optimization-based method. So this motivates us to propose a debiased inverse variance weighted estimator. And this is the most important slides of this talk. And if there's one page of the slides that I want you to take away, it's this one. So it's the d-IVW estimator only differ from the IVW estimator in the denominator. So we basically subtract the variance of the little gamma j hat from the denominator. And in this way, the d-IVW estimator corrects the bias of the IVW and becomes substantially more robust to many weak IVs. So in order to see that, we can also calculate the difference of the d-IVW estimator with respect to beta 0. And then we can calculate that the expectation of the numerator is not exactly 0. And we can study the asymptotic distribution of the d-IVW estimator. So basically in regime A, if we have kappa times root p goes to infinity, where kappa is the average IV strength and p is the number of SNPs. So if this holds, and if all these technical conditions hold, then the d-IVW estimator is consistent and asymptotically normal. And if we only assume this condition holds, then the d-IVW estimator is consistent. Let's compare this with the IVW estimator. And comparing these two theorems, we see that the d-IVW estimator is consistent and asymptotically normal in regime A, B, and C from theorem 1, whereas the IVW is only consistent and asymptotically normal in regime A. And because the d-IVW estimator covers until regime C, so this covers basically the common scenarios that we encounter in practice. So the d-IVW estimator is usually quite robust to the many weak IVs. And the variance also has an explicit form and can be consistently estimated. A little more discussion on this condition, kappa times root p goes to infinity. Again, the kappa times root p goes to infinity is likely to hold in MR analysis because, for example, if all the IVs are weak in the sense that each z-score is in the order of the constant, then we only need the number of such weak IVs goes to infinity. And also incorporating many weak IVs into the d-IVW can improve its performance. And this condition is also imposed by other methods that are robust to weak IVs, for example, the limo and the MRREPs. But limo requires individual data and MRREPs requires common variance. And this condition can be checked by empirically by assessing this average F statistic -1 denoted by kappa hat times root p. And now let's move to the second challenge, the pleiotropy. So to deal with pleiotropy, let's also start from the linear structural equation. Now in the outcome equation, we have the direct effect of this SNP on the outcome, even we have condition on the exposure variable X. And in this case, we also plug in the exposure equation into the second one, and then we obtain that the effect of Zj on the outcome, which is the capital gamma J, is beta 0 times little gamma J plus the alpha J. And this motivates the following assumption, which is able to deal with the balanced horizontal pleiotropy, which basically differs from the previous one in that here we allow this alpha J to be non-zero, but we assume that it's a balanced horizontal pleiotropy, which means the alpha J is ID from normal with mean 0, and also the alpha J is independent with the IV strength. And we can still show that the d-IVW estimator is consistent and asymptotically normal under this setting, but its variance is larger because of the random effect alpha J's. So now we have talked about the d-IVW estimator. Now what's next is that we propose methods to do the hard thresholding to improve the efficiency of the d-IVW estimator. So the d-IVW estimator usually does not need screening to reduce bias, which is unlike the IVW, but filtering out irrelevant SNPs can improve its efficiency. And to avoid winner's curse, we recommend using an independent selection data set to do the hard thresholding. So formally, we use a selection data set, which looks like this, and then we calculate, then we set a z-score threshold lambda, and then we have a set index, which tell us which SNP passed the z-score threshold based on the selection data set. And based on this index set, we calculate the DIVW estimator using the exposure and outcome data sets. And how do we choose this z-score threshold lambda? So the common choice in practice is 5.45. This corresponds to using the p-value threshold of 5 × 10⁻⁸. And this is actually a too stringent threshold because it's originally proposed to reduce the false discovery rate from the GWAS study from testing hypothesis many times. But it's not applicable to our case and does not adapt to the number of SNPs. And another natural choice is the root of 2 × log p. And this adapts to the number of SNP we have, but it's still too stringent because although it guarantees the probability of selecting null IVs being very small, but that's not our goal. Our goal is to reduce the variance of our DIVW estimator, but not controlling the false discovery rate. Given that our goal is to reduce the variance, so we propose an algorithm called MR estimation optimization algorithm, which can determine lambda adaptively. So the intuition is that we want to choose a lambda that directly minimizes the variance, but the variance depends on the true parameter beta 0. So the algorithm is very simple. It alternates between estimating beta 0 and finding the optimal lambda. Next, before I move to the simulation, I'll pause here to see if there are any questions.
Hi, Ting. I have a question about the estimator. Can you go back to the slides showing the DIVW estimator?
Mm-hmm.
So you're doing a like debiasing on the denominator, right? So you basically well, would you worry about, say, after you basically minus this, the minus like that number, do you worry about like having like negative signs in the individual terms of the denominator? Does that, I mean, would that cause any trouble?
That's a great question. So first of all, we do not worry about each individual term being negative, but we will be worrying about like the sum of this being negative. But that's ruled out by the condition of kappa times root p goes to infinity. When that's true, it's like with probability going to 1 that this denominator will be positive.
Okay, thank you. I do have a related question. So you showed that the IVW estimator converged to, say under like that regime, converged to like a scaled version of beta 0, right? So,
yes.
So basically, so can you just maybe just multiply, say, your IVW by that, like, and well, I guess you have the maybe the next slide, or basically you say, okay, so the asymptotic bias is, yeah, say the kappa plus 1 factor. So is it, say, I like, can you basically just
I see your question. So I think you were asking, like, can we use the asymptotic bias to debias the IVW estimator? So because this bias, it depends on beta 0, so we cannot directly use this to debias the IVW estimator. And what we are trying to do in a DIVW is so actually trying to debias without knowing the beta 0.
Thank you.
Yeah, thank you for the question. Okay, I'll first move forward, but I'm very happy to answer any questions at the end. So let's show some simulation results. First, to closely mirror what's done in practice, we take the real BMI and CAD data set as our simulation parameters. And in the data set, we have a selection data set, exposure and outcome data set. And the selection data set is GWAS for BMI in the Japanese population. And the exposure data set is the GWAS for BMI in the UK Biobank. And the outcome data set is the GWAS for CAD by the Cardiogram plus C4D consortium. And we obtain from these three data sets the standard error parameters. And also we obtain from the exposure data set the marginal association statistics as our little gamma j, the true value of the IB strength. And after applying standard data pre-processing and LD clumping, there exists in total 1,119 independent SNPs. And we set beta 0 equals 0.4, and the capital gamma j is beta 0 times little gamma j. So this is the scenario where we have no pleiotropy, but the case with pleiotropy is in the paper, and the results are similar, so I'm not showing those here. We consider a first simulation scenario where we have many weak IVs and no null IV. And first, I'd like to mention that a DIVW estimator can be very easily implemented. It basically just needs one line of code. And in this simulation setting, we have this more than 1,000 genetic variants, and all of them are pretty weak. So the average IV strength can be calculated as 7.78. So it's reasonable to think that this is in the regime C that we have in the theorem 1, where the average IV strength is constant. But the condition that we require for the DIVW estimator to be consistent and asymptotically normal is the kappa times root p, which equals to more than 260. So it's reasonable to assume that the DIVW estimator has good performance guided by the theoretical results. So we compare 6 methods, and for each method we implement different IV thresholding z-score thresholding. And also we have the mean and simulation standard deviation and the estimated standard error and the coverage probability. So first we see that the IVW estimator without thresholding is biased towards 0 because the true value is 0.4. So this is consistent with our theoretical results. And if we do the thresholding and using these two methods to do the thresholding, then we are able to mitigate the bias. It's closer to 0.4 now, but the standard deviation is much larger. And the deep IVW estimator without thresholding with lambda equals 0 is almost unbiased, and its standard deviation is 0.054. It's like much smaller compared to the thresholded IVW estimator. And also its coverage probability is pretty good. And the DIVW estimator with this lambda equal to 5.45 or root 2 times log p are not recommended because they're trying to reduce the false discovery rate, which is not what we want. And we would recommend using the MREO algorithm to adaptively select lambda. And in this case, it chooses a lambda equals 0.03. So basically we does not thresholding away too many SNPs. And then the results are almost identical to the one without thresholding. And for the other popular methods, the MR agar, MR medium, MR mode, they are all biased if we have many weak IVs, so when lambda equal to 0. And especially the MR mode is pretty sensitive to the many weak IV. So the standard error is unreasonably large, and the standard deviation is also unreasonably large. And finally, we have this great method, the MR reps, and we also have 2 versions. So the first one is without thresholding, and the second one is using the empirical Bayes to have a spike and slap prior to do IV selection. And then we can compare the DIVW estimator with the MR reps, and they show similar performance in this setting. Let's see a second scenario where we have many weak IVs and many null IVs. And this is a more challenging setting because now we have more than 1,000 IVs that are irrelevant to the exposure and outcome, and only 10% of them are relevant IVs. So in this case, the average IV strength kappa is even smaller, it's 1.05. But the condition required for DIVW is reasonably large, is 35. So in this case, we see that the IVW without thresholding is even more biased with very small coverage probability. But the DIVW estimator still has desirable performance. And in this case, we can see that the DIVW estimator that use the MREO algorithm will choose a lambda close to 2. And in this case, it's able to threshold to screen away many irrelevant SNPs. And in this case, the standard deviation is much smaller compared to the IVW estimator, compared to the DIVW that use all the SNPs we have. And again, the other estimators are still similar to the previous one, and the MRREPS has similar performance compared to the DIVW estimator. And finally, I'll show the application of the results in the BMI and the CAD data set. And in this case, we use the true data, the selection and exposure and outcome data sets that are publicly available. And in this case, we still have this more than 100 SNPs, and the average IV strength can be estimated to be 6.78. And this condition is still more than 200. It's reasonably large for the IVW estimator to perform good. And here we can see that, so basically we still compare several methods, and we consider different thresholding scheme. And basically all the estimates are similar using different MR methods here. But the only different one might be the MR mode. So its estimator is quite large, but it's similar to what we saw in the simulation, that the standard error is unreasonably large if there are many weak IVs. And we have two versions of DIVW. So the first one is assuming no pleiotropy, and the second one is assuming there exists balanced horizontal pleiotropy. The estimators are exactly the same because it's the same formula, but the standard error are different. So the second one is larger because it needs to deal with the random effect of the direct effect. And so we also have a MREO. You use the MREO algorithm to select the IVs, and in this case, we choose a lambda that keep a little more than 1,000 SNPs, and the results are similar to the one without thresholding, and the standard error is also similar. So the DIVW estimator, the one without a pleiotropy and the one that assume pleiotropy have reasonable estimates, and the standard error is actually the smallest among all these methods, except for the IVW. And from our simulation results, we expect that the IVW is biased towards 0. And we can also propose a diagnostic plot, which can be used to validate assumption 1, or to falsify assumption 1. And the motivation of the diagnostic plot is that if the beta hat is close to beta 0, then we will expect the standard residual to follow a standard normal distribution. So we can make this QQ plot. And from this, in this real data example, the QQ plot looks very good. And so here are take-home messages for this part. So the IVW estimator is biased in presence of many weak IVs. And IVW with pre-screening does not resolve the bias. It's only a bandit solution. And we highly recommend the IVW estimator in mandated randomization. It is as simple as IVW with an explicit form. And it's a simple cure for bias from many weak IVs and balanced horizontal pleiotropy. And there's no pre-screening required for its consistency and asymptotic normality. Instead, the many weak IVs are helpful for DIVW. But if there are reasonable, if it's reasonable to think there are many irrelevant SNPs, then we can use the MREO algorithm to adaptively select the SNPs to improve precision. And this is also not an end, but a start. So the DIVW estimator can serve as the baseline estimator for investigating more complex settings. And we have an R package on GitHub. And finally, I would like to maybe take 5 minutes to talk about a recent work that's able to deal with more complicated pleiotropy pattern, which is called the Genius-Malwe estimator. So previously, we assumed that this direct effect of the SNP on the outcome, denoted by alpha J's, they are mean zero, and they are independent with the IB strength. So what is most crucial is that is this uncorrelated pleiotropy, which assumes the alpha J are independent with little gamma J. However, the MR Genius estimator, the Genius-Malwe estimator, allows for correlated pleiotropy. So in this exposure and outcome model, we put no restriction on the direct effect. And identification is from this estimation equation. We can identify the beta zero when the variance of X, the conditional variance of X given Z depend on at least some Z, which basically means the exposure variable is heteroscedastic. And so we can implement this Genius-Malwe method and compare this with existing ones in a real data set of the BMI and SBP application using individual participant data from the UK Biobank. And from these results, we can see that the Genius-Malwe estimator give a point estimate of 0.14 and the standard error is 0.069. So we are able to conclude at significance level 0.05 that the Genius-Malwe, using the Genius-Malwe estimator, that BMI has a significant effect on the blood pressure. And compare with these other estimators, the two-stage least square, the LIMO and IVW and DIVW and MR-REPS, all these methods assume that the direct effect require that the direct effect needs to be centered at zero. And when it is not true, so when it is not true, these estimators will be biased. And it's there are reasons to believe that these estimators are biased in this case because they all have the point estimator that are larger compared to the Genius-Malwe estimator, likely due to the direct effect of this genetic variance on the blood pressure. And the MR-Agar here is able to deal with non-mean zero direct effect, but in this case, it has an estimate that's similar to the Genius-Malwe estimator, but the standard error is much larger compared to the standard error from the Genius-Malwe. So if we use the MR-Agar instead, we are not able to conclude that the BMI has a significant effect on the blood pressure. Yeah, that's all I want to talk about. I will be happy to take any question.
Thank you, Ting, for the great talk. So time for questions. It used to be the students had priority. So are there any questions from students? Please unmute yourself. So. Or put your question in the chat. Okay, questions welcome from everyone, students and non-students.
Hi, Ting. Nice talk. This is Ali.
Hi.
Hi. So you mentioned that this setting where there are different populations that you estimate these different quantities. Are there any constraints on, for example, genetic ancestry in these populations? What are the constraints that you have on these different populations that, or different samples, I should say, that you use for estimation?
I'm not sure I totally understand the question. So are you saying that we use the selection exposure data set from different population and whether?
Yeah, so you have like selection data set, exposure data set, outcome data set. What I'm asking is, are there any constraints in terms of what these samples should represent? Should they all represent the same population? How much difference would be allowed
I see. Yeah, that's a great question. So for the selection data set, the selection data set is not as crucial as exposure and outcome data set, because the selection data set is only used to help us guide us through like which SNPs are relevant in the question of interest. So the selection data set is not as crucial, but it's very crucial for the exposure and outcome data set to share some similarity. And the similarity is basically that the genetic variant, so the SNP for the effect of the SNP for BMI and the effect of the SNP on CAD is similar for these two data sets. So that's the crucial assumption here.
I see. So selection is not very critical. I mean, the reason I ask is that you were using the Japanese data and the UK Biobank data, and I was wondering if the inherent differences in these populations might have an impact.
I see. Yeah, I mean, like the selection data set doesn't affect the results too much because
okay.
we're
that's great to know.
Yeah,
that's great to know. Thank you.
Yeah, thank you for the question.
Okay, other questions?
I have a kind of related question. I think you might have mentioned this earlier, but I think you said that the data within these data sets is aggregated, so it's not at the individual levels. What are the aggregation units that are actually used in the analysis?
The aggregation unit. Maybe I shouldn't say aggregated. Like so, the data from this summary, these data sets are only summary statistics of, for example, the BMI on each genetic variant. So we are only able to use those summary stats for estimation and inference, but not individual like exposure, individual's BMI and individual genetic data, etc. So we are only use this summary data.
I see. Okay, thank you. Really interesting talk.
Thank you.
Any more questions? Okay. So if there are no more questions, okay, let's thank Ting. Thank you, Ting, for giving our first seminar. And a quick reminder, there will be a special EDI seminar next week, and I really hope to see many of you there. Okay. Thanks, everyone.
Thank you for coming.
Again.
Thank you, team. Thank you, everybody. Bye.